We are going to practice drawing some nonpolar and polar neutral amino acids at different pHs. And the first one that we're going to do is serine. And we are going to draw serine 3 different ways. So first we're going to draw serine at its pI, so we'll just say at a pH of about 7. And then we're going to draw it at a pH of about 2, and then we'll draw it again at a pH of about 12. Now, when I'm being asked to draw an amino acid, I know that all amino acids have the same general structure. And if I know that I'm drawing the amino acid at its zwitterion pH, or another way of saying that is if I know that I'm drawing the amino acid at its pI, I know that this much of the amino acid is going to look like this. It doesn't matter what amino acid it is, it's going to look exactly like this when you are at the pI and you are being a zwitterion. So that much of it is very easy. As far as how do we make this serine, we need to refer to our chart of amino acids. Now, in your textbook, the table of amino acids that you have lists them alphabetically, which is really helpful for a problem like this, where you're looking for a specific amino acid, but it's not always helpful. It is handy to have several different charts. So I just found serine. It is right here. This is the one that we're drawing. And all that I'm focusing on is the R group right here because I've already drawn all the rest of the molecule. So the R group, CH2OH, that's the last thing that I need to fill in. CH2OH. So now I want to draw the serine at a pH of 2, and that is an acidic pH, which means when I'm dealing with acidic conditions, I'm only allowed to have positive charges. I'm not allowed to have negative charges anymore. So I am going to start by drawing that hydrogen up top because that's always there. That never changes. And because this is serine, my R group isn't going to change either. So that's going to be the second thing that I draw. Now, because I'm allowed to have positive charges, I know that my NH3 with the positive charge going to the left, that's okay. That doesn't have to change. That can stay the way that it is. I have to change the COO minus. It's not allowed to be COO minus anymore. So I have to get rid of the negative charge, and the way that I do that is by adding a hydrogen. So the COO minus becomes a COOH. So this is what we're looking at right here, this situation. COO minus becomes a COOH. Let's look at the next one, our next situation with serine when we're at a high pH. This is a basic pH, and on basic conditions, we're only allowed to have a negative charge. So let's draw what serine looks like under that situation. We've got that hydrogen up top. We know that the R group is going to be unchanged because that's what makes it serine, and we're allowed to have a negative charge this time, so the COO minus group is still there. So now we have to figure out what do we need to do to the NH3 plus group, because it's no longer allowed to be positive charged. We can't just get rid of the charge all by itself. The charges are changed with the addition or removal of hydrogen. So the getting rid of the positive charge on the nitrogen happens by removing one of its hydrogens. So this is what it looks like under basic pH. Now let's keep practicing this. You have a worksheet that has quite a few of these on it, a whole bunch of amino acids, and I've highlighted the ones that are nonpolar and polar neutral. So these are ones that we can start with right now. So for example, the first thing that we see here is that we have glycine. Without even knowing what glycine is, I know that there's going to be a carbon in the middle, there's going to be a hydrogen sticking up top, there's going to be some other stuff out here. I am at a pH of 3, which is acidic. So the acid is a pH of less than 7. And in that situation, we're only allowed to have positive charges. So since I have an acidic pH and I'm only allowed to have positive charges, I know that my NH3 group is okay, so I can go ahead and draw that. But my COO minus group is not going to be allowed. It needs to be converted to COOH for this acidic pH. And then what about the R group? How are we going to figure out what the R group is? Well, to do that, we need to take a look at a table of amino acids. So I'm going to flip back over here, and we are looking for... Is it glycine? I think it's glycine. It's something. We're looking for glycine, I think. And it looks like it's up here, if I remember right. This is the one that we're looking for. And this is the littlest of all the amino acids. So its R group is just a hydrogen. So let's go back and see. Yes, it is actually glycine. And there it is. There's its structure. Let's try one more of this before we move on to something else. So for our next example, we have valine. So we know right away, no matter what, that we've got this carbon in the middle, and we've got a hydrogen up top, and we're going to have a few other things attached. What's our pH for this guy? A pH of 8. That means that it is in a basic condition. So a basic means that you have a pH above 7, greater than 7. And under basic conditions, you're only allowed to have negative charges. So when we're looking at our amino and our acid group, our COO minus is allowed to be COO minus, so that's fine. But the NH3 plus group is not allowed because positive charges are not allowed. So to get rid of the positive charge, we have to get rid of one of its hydrogens right there. And then for the R group for valine, we need to go back to our table, find valine. Where is valine? Valine is, looks like it's right here. CH3, CH with 2 CH3s coming off of it. CH with 2 CH3s coming off of it.